Lecture 5. Hello, everyone. This is what I have on the agenda for today. And there isn't really any new fundamental additional piece of information that we're going to be talking about, but it's more about formalizing what we have already seen in the context of a few examples over the past couple of days. Okay? So we are concerned about, or concerned with first-order time-dependent circuits. These are circuits where essentially the behavior of a variable of interest, something that you're trying to find, like a voltage or current as a function of time, is going to be described by a first-order linear differential equation. And so typically you would see this with a circuit that has one capacitor or one inductor. It does not have to be limited to one capacitor or one inductor. Depending on how the circuit is, you might have more than one capacitor or inductor and still have a first order type of behavior. But the simplest case would involve one. So we will try to think about how to approach this problem systematically. And for that, we'll pay special attention to the behavior of capacitors and inductors when a change in the circuit happens. And of course, the way they behave also when the circuit is sitting for a long time without any change. And again, these are things that we saw in the context of examples in the past couple of days. We will define the concept of time constant and initial value and final value. That really have to do, again, with what happens during switching or in DC steady state. Okay? So a first-order time-dependent circuit, I'll just give you this as some sort of a definition, if you want. First-order time-dependent circuit. And I'll emphasize that we are dealing with linear circuits at this point. So this is a circuit where the behavior of voltages and currents is described by a first-order linear ordinary differential equation. And I put this ordinary here because all your voltages and currents are functions of time, but time is really the only variable. They could have parametric dependencies on other things. So you could have, let's say, a resistor in the circuit, and if you change the value of the resistor, of course, the answer changes. But the functional dependence that underpins that differential equation is dependence on time. This is the case for the type of circuits that we deal with here. Maybe in parentheses here, I should say that if you go to circuits where you're dealing with frequencies in signals, such that the wavelength of the signals involved is actually comparable to the circuit dimensions or larger, then you really are dealing with electromagnetic waves traveling all over the circuit. And so examples of these are in microwave waveguides. And then you actually have spatial dependence as well. Okay. Here we are not dealing with anything like that. We're dealing with circuits where we are just concerned with a dependence on time. So our wires, no matter how long the wire is, everywhere on a wire has the same voltage. But that voltage changes with time, or the current going through the wire changes with time. Okay. So that's what we mean by first-order circuits. And like I said, typically you would encounter something that has one capacitor or one inductor, or a simple combination of capacitors or that of inductors. Now, the systematic approach to solving these circuits is nothing new. You have to write your KVLs and KCLs. Maybe what to keep in mind is that typically, when you want to solve for this, if you are concerned with finding, let's say, the voltage of a capacitor as a function of time, it's normally handy to try to rearrange your equations so that you end up with a differential equation that directly has the voltage of that capacitor in it. But so I'll just summarize here the systematic approach. Write all the KVLs, KCLs, and element relationships. Now, you want to do this, let's say typically, like in the examples that we saw, you have some sort of a transition happening. For instance, you had a current source whose value jumped from 0 to I naught at time 0. Okay? Or there could be any other number of changes. So you want to start from before any such switching or transition has taken place. So do this first for before any switching has taken place. Okay. Then solve these equations to get whatever you're interested in for that period of time. So solve the system of equations to obtain the variables of interest. Then think about what happens during the switching or transition. So now you've reached a point where a current is being changed, a voltage is being changed, a switch is being opened or closed. Any of these would lead to now a series of other events in the circuit. So it would set a transient behavior into motion. Okay? So now look at what happens during the switching activity. So in other words, you have to now carry or start with what you found just before switching, and from that conclude or find the value of the variables of interest just after a switching behavior has taken place, right? So deal with the switching behavior. or with the switching activity. That means find out how the variables of interest change from what they were just before the switching activity took place. So if you're dealing with some abrupt change, you're really looking at what happens in no time at all, from just before to just after that change. Now, if a change in the circuit has happened, in principle, you have a new circuit on your hand. So it could be a simple switch being opened or closed, but it could make a substantial change to your system of equations. It's not the case that all your KVLs and KCLs are necessarily going to change, but a good number of them might. Okay? So as a general rule, it's good to not assume anything, especially as you start and practice, and just now treat the circuit as a new one, rewrite the KVLs and KCLs for it. You can't go wrong that way. You might spend another extra minute on it, but it reduces the chances of making mistakes significantly. Okay. So basically, we'll go back to point number one. Write all the KVLs, KCLs, and element relationships now for this new circuit. For this, I'll say, new circuit, since at least some of the KVLs or KCLs might have changed due to this switching activity. Okay. Now, because you created a change in the circuit, it will take a while for the circuit to settle back or to settle down, rather, because it's not necessarily going to go back where it was, to settle down and reach a DC steady state where nothing changes. And so that duration of time, that's called the transient part of the behavior, or the transient response. And that is going to be described by your differential equation. So now you have to arrange all these KVLs, KCLs, and element relationships and play with them and eliminate things between them until you get a differential equation, hopefully for the variable you're interested in. So or rather, I should say, eliminate variables among the equations until you are left with a first order linear ordinary differential equation for one variable, one unknown, and preferably the variable that you're directly interested in. It doesn't have to be that way. Sometimes you might find it more convenient to find first the answer for some current somewhere else, and then use that to find the voltage somewhere else. So it doesn't have to be directly the variable that you want from the beginning, but preferably that. And finally, use what you found in the previous step, or 2 steps before, where we said deal with the switching activity. Use the outcome of that as the initial value for solving this differential equation. Use the outcome of your analysis of the switching activity as the initial value needed to solve the above differential equation. Okay, that's it. Now, I hope this sequence of events makes sense to at least some of you, because this is essentially what we did during the examples. But if not, that's fine. We are going to start looking at some examples where we will just follow these steps, and then hopefully it will make sense. I think there was a question somewhere here. Yeah.
Yeah. How does the element relationships, how are those going to change?
How are the element relationships going to change during the switching? That's a good question. A lot of them won't. So let's say if you have a capacitor, unless you make a physical alteration to that capacitor, it's not going to change. A resistor, an inductor, right? So the element relationship that is changing is, so let's say you have a switch, right? And you open the switch. Well, the element relationship for that switch was, before it was closed, so it took no voltage, and it could let any current go through, right? Now it's open. So that's really what has changed, right? So that switch now has 0 current, and there could be any voltage across it. Or you could have a current source that has gone from -2 amps to 3 amps. So the value of the current has changed. So it's a minor change, although it would have major consequences, right? Anything else? So this is, and again, I don't mean this as a recipe. This is really something that hopefully with practice, well, it's just a systematic approach based on KVL and KCL. You will develop a natural ability to do this. You shouldn't need to go through this list and memorize. But as a sort of guideline here is what I meant. Okay. Then the behavior of capacitor and inductor during switching and in DC steady state. Well, the element relationship for a capacitor is just one statement, right? What is it? Well, I equals C dV by dt, right? So the capacitor, and pay attention to the polarity, right? The way I'm used to defining polarities is if I define the voltage like this, and not just me, this is common practice. Very commonly, we also define the current in that direction. But both voltage and current can be positive or negative values, right? If I write it like this, then I equals C dV by dt. It follows immediately from this that if you are going to change the voltage of the capacitor abruptly, which means dV by dt is going to be infinity because you have a finite change over no time, then that requires infinite current in the capacitor. And the analogy, again, going back to the bucket of water, I have an empty bucket of water, and I wanted to, the water level to go from 0 to 1 meter in no time at all. How much? What's the flow of water that I should put in? A lot, meaning infinity, if I want it to happen in no time at all, right? If you want to fill up your bottle in no time, you need an infinite flow of water. So same thing here. So, and for that reason, a capacitor will obviously prevent or resist an abrupt change in voltage, unless you somehow force it, which again, as we've seen in examples in the past, you should not do in real life, right? So a capacitor will resist. Now, I'm hesitant to say resist. I don't mean this in the sense of resistance, the way a resistor works. Will, I don't want to say oppose, will show hesitation to, or it's more than that. Will protest. I don't know. Take any of these. Maybe I'll say resist, and hopefully we won't treat it as in the sense of a resistance. Will resist an abrupt change in voltage because for that it would need infinite current. It's not to say it never happens. If you put a voltage source across a capacitor and change the voltage of that source abruptly, well, it's forced on the capacitor. But you can do that only on paper, not in real life. Okay. What about during long-term DC steady state? Now, by steady state, we mean when things are not changing. And I want to emphasize we are concerned with DC steady state because sometimes you could refer to a situation as being in steady state where maybe you have a periodic change of things, like an AC situation. But we are concerned with DC. So when things are not changing with time at all. If things are not changing with time, you see from the same equation, everything is going to be constant with time. dV by dt is 0. The current is going to be 0. In DC steady state, therefore, the current of a capacitor is 0. It acts like an open circuit. What is the voltage across a capacitor in DC steady state? Who says 0? Who says infinity? Well, the rest say none of the above. Yeah. It can be anything. It depends on what's happening in the rest of the circuit. Okay? It's essentially an open circuit, and there could be any voltage difference across it. So in DC steady state, so that was one point. Or maybe I should, just to be consistent. Capacitor in DC steady state dV by dt is going to be 0, so I is going to be 0. Which means it will act like an open circuit. No current. It can have any voltage. And that is based on what the rest of the circuit requires of it. As required by the rest of the circuit. So that's the capacitor during switching and in DC steady state, when it has been sitting for a very long time in a circuit without any change. Yes?
Can we say that any voltage in the capacitor is a result of the trivial differential equation dV dt equals 0?
Any voltage in the capacitor is the result of this dV by dt equals 0. The answer is that was the question. The answer is any voltage, any constant voltage in the capacitor is consistent with this. Does not contradict this, right? Because as long as V does not change, whatever constant it is, dV by dt is equal to 0. But it's not the result of this, or it's not purely the result of this, because this will not impose any particular value. Rather, it's the result of this, which tells us I equals 0, together with all the other pieces of information in the circuit, all the KVLs, KCLs, and element relationships. Okay? It's the result of the solution of the circuit, which involves everything, not just this. So let's write down what the inductor does. Inductor during switching. Now, an inductor, again with a similar convention for the direction of voltage and current, you have, it's the opposite. Instead of the current being the derivative proportional to the derivative of the voltage, in the inductor the voltage is proportional with the derivative of the current. Okay? So the way we approach thinking about it is very similar to the other one. An inductor will resist or oppose an abrupt change in the current, because an abrupt change in the current means di by dt is infinity, which means the inductor would require an infinite voltage. Okay? So in the same language that we wrote up there, an inductor will resist an abrupt change in its current because that would require an infinite voltage. And finally, inductor in DC steady state. In the same manner, but in this case, the equation has the time derivative of the current. DC steady state, nothing is changing with time. di by dt is 0. And that will, for the inductor, mean that its voltage is 0. So it will act like a short circuit. There's no voltage drop across it. But it can have any current as required by the rest of the circuit. Zero voltage drop, but can have any current as required by the rest of the circuit. So this is the complete picture.
So why don't we talk about an inductor responding to an abrupt change in voltage?
Why don't we talk about an inductor responding to an abrupt change in voltage? Any thoughts about that? That's a very good question. Yes.
Because our mathematical relationship doesn't tell us anything about that case?
Yes. The relationship doesn't tell us anything about that case. Or maybe to put it in a more easily acceptable manner, there's nothing that the inductor imposes. In other words, an inductor has no problem having an abrupt change in voltage. Similarly, a capacitor has no problem taking an abrupt change in current. Again, let's go back to the analogy of the bucket of water. So you go to the kitchen sink, right? Imagine the sink basin being the capacitor, right? The current going to it is 0. The tap is closed. And you abruptly open the tap. You change the current that goes to it. No problem with that at all, right? You change the current abruptly. What you can't change is how much water there is in it, because that takes accumulation over time, right? And similarly, then, the inductor does not care if you change the voltage across it abruptly. If you change V abruptly, all it means is that the time derivative of the current also changes abruptly. But that's quite OK. Yes, yes. So then, so let's say you had some circuit. Imagine you had a circuit where an abrupt change in a voltage somewhere would require a correspondingly abrupt change in an inductor current, right? Then, of course, the inductor would oppose that. Not because it cares about that abrupt change in voltage, because it cares about the abrupt change in current. So how can current flow if there is no voltage drop? The way it does in a wire. Okay. Now, at the circuit level, when we have this picture of ideal wire with 0 resistance, that's in fact what happens. Think about the wire being like a resistor, but with R equals 0. So the current is V divided by R. Now, if R is 0, with V equals 0, you can still get a current, right? Because that's undefined. Could be any current. In reality, though, there is no ideal wire. Or at least for common materials that we work with. We are not talking about superconductivity here. But a typical wire would have some resistance. So even a good wire would require a very, very, very small drop of voltage across it. But it would be very small. So typically, a good wire would take a voltage drop that's negligible compared to whatever else you have in the circuit, and that's why it's neglected. And we idealize that by using this simple ideal wire picture. So this is the summary of what happens during switching and in DC steady state. So what I want to do now is really put these to use. Okay. And maybe after solving one example, we will talk in a little more detail about this time constant and initial value and final value. But it would be easier to do so by looking at an example. So I want to now look at an example that involves a capacitor in this case. We already looked at a circuit that involved an inductor on Tuesday. So this time, let's look at a circuit that involves a capacitor, but do it more systematically along the lines of what we discussed here. So consider this. I'll put a voltage source here, let's say, with value V0. I'll put a switch here. A resistor and a capacitor. Let's call this R, C. And this switch will be closed at time t equals 0. So this symbol, t equals 0, put on top of the switch here, indicates that at t equals 0, someone has closed the switch, turned it on. So the question is, if we call this VC, if we call this IC, and VR and IR, the question is, what is VC of t? And if I say VC of t without specifying any particular range for t, I mean from minus infinity to plus infinity. Or I shouldn't say from minus infinity, but maybe from as far back as you can think of, all the way to as far forward as you can think of, okay? Including what happens during that transition. So let's try to apply the set of guidelines that, or steps rather, that we came up with here. First of all, number one, we are trying to understand the circuit before any switching action took place. So writing all the KVLs, KCLs before that, solving the circuit to find the value of VC, the voltage across the capacitor, before any switching action took place. Okay? So let's see what I have there. So first, before switching. So t less than 0. So the circuit has been sitting like that for a very, very long time. You see, there's a constant V0 applied here, let's say 1.5 volts. And there's nothing changing in the circuit. It's been sitting like that since the origin of time. And it has had enough time to reach a DC steady state. Nothing is changing with time. So I'll write that down. Sitting without any change for a very long time, and is in a DC steady state. Well, this is not a very difficult circuit to solve. How many nodes do I have here? Well, let's count. I have a node here, one node here, one here, one here, and one here. 4 nodes. So I get 3 KCL equations, 3 independent KCL equations. Mind you, they are very simple and straightforward. So, you know, if you think about, maybe I should move this a little bit this way. So you could call this IS, the current in the switch. Now you know that's 0 because the switch is open. And you could call this, let's say, let's call it IV, the current of the voltage source. So you would have the KCLs that tell you minus IV minus IS is equal to 0. So this might be a little boring, but just to show you that these things exist, I'll write them quickly here for your reference. So KCL, you have minus IV minus IS equals 0. You have IS, the current of the switch, minus IR equals 0. And you have IR minus IC equal to 0. So yeah, these are trivial, but it's good to have them as reference. And the last one will not give you an independent equation. How about KVL? I have just one loop. Can you guys write down the KVL for this? "20 seconds. Write down the KVL for this. Who has it? Show of hands. Who has written the KVL already for this? Okay. So this is worth maybe a little bit of attention. So I assume that those of you who have had difficulty with this, your problem has been with the switch, because the VR and VC and V naught are, well, you know, they're quite well defined there. What I want to point out is that the switch is no different. The only difference here is that I haven't given its voltage a name, but that has been maybe my oversight, right? There's nothing about the switch that would make it awkward to write a KVL. You just have to give its voltage a name like everything else. So maybe I'll give it a little space here. So this is IS, and this is the voltage of the switch. Let's call this VS. A switch can have any voltage when it's open, So now let's write the KVL. Minus V naught plus Vs plus Vr plus Vc equals 0. That's the KVL. How about element relationships? Well, we have the V naught, the value of V naught. So that's the voltage of the source. We know that the switch is open, right? So Is is 0. This is an open switch. So that's another element relationship. We know that VR, VR equals R times IR. And what else do we know? We know that IC equals C dVc by dt, which, because of DC steady state, since there is no change, the capacitor current is also 0, since things are not changing with time. dVc by dt is 0, and therefore the capacitor has no current. This is all the equations. Now, from these, we would like to find out what the value of Vc was. Try it on your own. See what the value of Vc is by solving the system of equations. Does anyone have an answer? So that's one suggestion we have here, Vc equals V naught. Anything else? Anyone agrees with that? Vc equals V naught? Any other answer? Well, let's try to solve it. Or solve the system. So let's start with the things that we do know. V naught we know, that's a known parameter of the problem. Is is 0, it's a piece of information. So if you look at the KCLs, for instance, immediately from there you conclude that IV is equal to 0, which you might say it's trivial because, yeah, you have the source here. And if the switch doesn't allow the passage of any current, then the source cannot have any current going through. So IV equals 0. Again, if the switch is open, Is equals 0. From here, we have IR equals 0. Again, you might say it's trivial. The resistor has nowhere else to send its current. IR equals 0. And from IR equals 0, then the third KCL tells you that IC is equal 0, which is fortunate because that's compatible with what we expected for the capacitor down here in VC steady state. So the KCLs tell you that, yeah, all these elements have 0 current. That's good. If you look at Ohm's law for the resistor, you see that the resistor also has 0 volt drop across it because its current is 0, and so its voltage is also 0. So all you have left is the KVL. Now look at the KVL. V naught is a known quantity. VR is 0. What is Vs? We don't know. Can be anything. The switch doesn't impose anything. And what is Vc? Well, that's what we are interested in. We don't know. You're left with two equations in this. One equation in this case and two unknowns. And that's all you've got. You saw I already used up everything that I had. So what do I do in this case? Yes. Things sitting flat, steady state. So you are asking for a piece of information that you need, basically, right? So this does not give me enough. I have to tell you if the capacitor had some initial charge or not, right? So I haven't given you enough information in this case. It's again like a bucket of water. If I give you a bucket of water connected to to some pipes, and I ask you how much water was in it. You say, well, how do I know? Tell me if you had put anything in it at the beginning, right? So what the circuit tells you is, depending on how much, to what voltage you had charged the capacitor initially, then that will determine the voltage that the switch has to see. But VC cannot be extracted from this. For this particular example, and this is not always the case, but for this particular example, you actually need to know what the capacitor's charge was. Imagine you have built this circuit, you haven't closed the switch, you have connected things together. If that capacitor had one coulomb of charge accumulated in it 100 trillion years ago, it would still have it now, before the switching. Okay? So VC, so let me write this down. In this particular example, a piece of information is missing. What was VC when everything started? Because the current through the capacitor is 0, whatever value of VC you had will stay there, because the voltage will not change. So you need that info. Okay. So let's assume I've given you that value. Let's call it VC at 0 minus. Okay. So this is just an analysis of what was going on in the circuit up to that point. And in fact, the KVLs and KCLs were not really helpful in giving you what the charge of the capacitor was initially. That's something you had to know, like the bucket of water. But on the other hand, they are useful in knowing VC in telling you everything else, such as the voltage across the switch. Because you see, Vs is not 0 nor infinity. Minus V naught plus Vs plus Vr, which is 0, as we argued, plus Vc, which is this Vc of 0 minus. That has to be 0. So that tells you that Vs is actually V naught minus Vc of 0 minus. So the switch is taking that voltage difference, whatever voltage difference is needed. Okay, so I think we can take a break here before the transition happens. We just analyzed the circuit at time t less than 0. So this was going on the time axis all the way to the point of just before time t equals 0. Okay, so this behavior continued until time 0 minus. And that's why I called this value Vc of 0 minus, because things were not changing up to that point. Okay, now from 0 minus to 0 plus, something very significant takes place. And that's the closing of the switch. Just before t equals 0, the switch was open. Just after t equals 0, the switch is closed. So the circuit has entirely changed. A closed switch now acts like a wire. There is no voltage drop on it, and it can allow any current to go in either direction. So the circuit is different. So our next step, if we follow what we set up here, is, so we've gone through the first step. We analyzed the circuit before 0 and solved the system of equations and saw how to deal with that. Now we are at this point, deal with the switching activity, how things have changed going from 0 minus to 0 plus. let's see what are the things that we know about each element. We know that the voltage source just applies V naught. It's like a battery. It's sitting there. It's not undergoing any particular change. It's V naught. Well, the switch, we know it goes from an open circuit, which means it could have any voltage but no current, to a short circuit. Now it can have any current but no voltage, so 0 volt drop. The resistor is a very accommodating element, you might say. V equals Ri, but before the switching had 0 current. After the switching can have some current, can have some voltage, and is completely happy having an abrupt change. The resistor does not impose anything as far as abrupt switching is concerned. It can have a sudden change in current and a corresponding sudden change in voltage. How about the capacitor? What is it that the capacitor does not like? So remember, I equals C dV by dt for a capacitor. So the capacitor does not like a sudden change in voltage, because that would require infinite current, like we saw before. So now going from t equals 0 minus, this is our next step. To t equals 0 plus. Okay, so we started first before switching. That was, you might say, step 1. Then going from t equals 0 minus to t equals 0 plus, the capacitor does not like a sudden change in voltage, as we just discussed. Which means then, in mathematical language, Vc at 0 plus, so immediately after switching, is equal to Vc 0 minus. Whatever it was, to whatever value level it was charged, it's like the sink example again. Let's say you had some amount of water in the sink. Now you open the tap. Just because you open the tap, the level of water in the sink doesn't change immediately, right? That's still the same. Now you have to give it time before it fills up. So Vc plus equals Vc minus. So if you knew Vc plus, if you knew Vc minus, which was a piece of information that you had to be given, then you know Vc plus. So now let's draw the circuit at time t equals 0 plus, the full circuit. At t equals 0 plus, the circuit looks like this. You have the voltage source. We have the switch that has been closed. So I'll just draw it like this. It's still there, but it's been closed, so it's effectively a wire. Have the resistor, the capacitor. So this is R. Now this is Vc. At time t equals 0 plus, so this is the value of Vc at t equals 0 plus. At 0 plus, which, as we just argued up there, equals Vc of 0 minus. It's the same value because the capacitor will oppose a sudden change in its voltage. Well, what does that tell us for the rest of the circuit? For instance, the value of Ic. Or Vr. Or Ir. So what is the value of Ic? Or Ir? Well, we have a circuit. We happen to be interested in it at one particular moment in time, t equals 0 plus. Again, KVL, KCL, everything is fully applicable. So KCL tells you, for instance, that IR minus IC equals 0, or IC is just IR. Nothing new, trivial. We saw it before too. Okay. So if I write a KVL here, I have minus V naught plus VR plus Vc of 0 minus equals 0. And element, of course, we know that VR is RIR. So from here you can simply calculate VR because it's V naught minus Vc of 0 minus. And from here you can calculate IR, which then simply is that divided by R. And that IR also is the same as IC. They have the same current. So this is how you have basically fully analyzed this circuit at that point, at the point t equals 0 plus in time. Now maybe you didn't care about knowing the value of the capacitor current or resistor voltage. Maybe I just wanted to show you that you can do a full analysis. Okay. It might be that for our purposes they were not needed specifically. But this is what's happening at t equals 0 plus. You might say the really interesting action starts at t equals 0 plus and going forward. So now that's what we are going to deal with. That's the next step. Again, going back to our original list here. We dealt with the switching activity. Now we know how things are at 0 plus. From this point forward, the circuit configuration is not changing anymore. I have closed the switch. I'm not touching it anymore. I'm just letting it now relax on its own, go through its transient. And so again, I'm back to writing the KVLs and KCLs for the new circuit and element relationships, and now playing with these equations until we are left with one ordinary differential equation. So now I will say at t greater than 0, which means from the point t equals 0 plus forward. The circuit is still the same. The circuit is still the same, but the value of Vc is going to change. Now gradually there is going to be some charging or discharging activity in the capacitor. So write your KVL, KCLs, and element relationships, and simplify the equations, eliminate variables, until you get a differential equation that has Vc in it. So I'll draw the circuit here for the reference again. Now this Vc is not Vc of 0 minus anymore. It's going to change. It starts from that, but it's going to change. Vc. This may be a good time to look at it together. And by the way, I haven't indicated the current through the source here because I'm not concerned with it. If we wanted to calculate it, of course, you could write a KCL up here, and you would see that it's equal to the current in the resistor. It's equal to the current in the capacitor, maybe with a minus sign depending on your direction. But anyway, so the KCL that we saw before tells us IR is the same as IC, right? Let's just remember that. And the KVL is minus V naught plus VR plus VC equals 0. And the elements, well, one is just the value of V naught. Another one is VR equals RIR. And another one is IC, which is the same as IR, equals C dVC by dt. So I don't really have a whole lot of equations. Maybe let me just replace IR with IC. So could say this one says VR is also equal to R times IC because of that KCL. So how do I combine these to get one equation that has VC in it? And that will be a linear differential equation that I can solve. This is something that comes with experience, and you do it by inspection. So let's look at the first equation. Well, the KCL, I have already implemented it. IR equals IC. The KVL, minus V naught plus VR plus VC. It already has a constant, V naught. It has the variable of my interest, VC, and it has VR. Well, if only I could write VR somehow in the form of VC, then I think that's it, right? I'd be there. I'd have an equation that has only VC in it, right? Can you guys tell me how to write VR in the form of VC, or based on VC? Yeah, look at here, use IC. VR is simply R times IC, and IC has that. So from here, I have VR equals R times IC, which is C dVC by dt. Now, if I take my KVL, let's call that equation 1, and let's call this 2. Now, 1 and 2, or 2 put in 1, gives me minus V naught plus RC dVC by dt plus VC equals 0. Okay. And maybe to make it look a little nicer or more conventional, I'll just rearrange things. I'll say dVC by dt plus 1 over RC VC equals V naught over RC. R, C, and V naught are known parameters of the problem. This is a first order linear ordinary differential equation in VC as a function of time. Maybe let me spell this out. Now, last time we saw another example of this, and this is the kind of thing that you're doing in your differential equation course anyway, and you're learning systematic approaches to solving these equations. I just told you what the general form of the answer for these equations is. So this is just a general form of the answer. It involves an exponential decay with some factor, with some constant. Now, last time I wrote this as e to the minus alpha t. a more insightful way is to write it like this: e to the minus t over some factor, tau, which we'll call time constant, and we'll soon see why. But this tau is a parameter of the problem, plus b. So this is the general answer. General solution. What you now have to do is to find the value of a, b, and tau. Now, how do I find the value of tau and a and b? Well, this is a general form of the answer, but we know that it has to satisfy for us this particular equation that I have in the box up there, right? So there are parameters in there, r, c, and v naught. So for this to work in that equation, well, I'll just put it in and make sure that things are consistent, right? So plug this in the differential equation. So if that's the form of VC, the first derivative is going to be minus a over tau e to the minus t over tau. And the derivative of b, b is just a constant. The derivative is going to be 0 plus 1 over RC times the whole thing, VC, which is a e to the minus t over tau plus b equals v naught over RC. Let's see what a, b, and tau should be so that this equation is satisfied. I'll rearrange a little bit, just like I did in the other example last time. So here I can factor out a e to the minus t over tau, and I'll have minus 1 over tau left from the first term and 1 over RC left from the second term. And then I have plus b over RC equals the other side. For this to work, the right-hand side, v naught over RC, is just a constant. These are constant parameters. Whereas the left-hand side has a part that depends on time. And this has to work for all time t, right? So I can't have something on the left that depends on t and changes with t equal to some constant. So the first term, the time-dependent term, has to vanish. So this has to be 0, which means the only way to ensure that for all time t is that this factor, minus 1 over tau plus 1 over RC, has to be 0. For this to work for all time, in this case, all the positive times, greater than 0 that we're concerned with, we need to have minus 1 over tau plus 1 over RC equals 0, so that the time-dependent term from the left vanishes. And then all I have to do is to make sure that b over RC is equal to v naught over RC. That's easy enough. B should be equal to b naught. So from the first one, I get tau should be equal to RC. From the second one, I get b should be V naught. So I'm getting pretty close, because it means now that my solution up there, Vc equals A e to the minus t over tau plus b. I already found tau, and I already found b. So I'm almost there. Vc of t equals A e to the minus t over rc plus v naught. So I'm getting the answer in parametric dependence on r, c, and v naught. Trouble is, I still have one constant, a, that I have not found yet. Where do I get that? Any suggestions? The initial, from the initial value. And I think this is the kind of thing you see in your differential equations course. Excuse me. When you solve a differential equation, you might have to deal with an initial value or a boundary value. So in this case, what is my initial condition? For all times t greater than 0, what was the initial point? It's t equals 0 plus. That's the beginning of t greater than 0, right? So I need to apply my initial, now apply the initial condition. Which was the value of Vc at point t equals 0 plus. Now, in this particular case, because this was a capacitor, during the transition from 0 minus to 0 plus, its voltage didn't change. It didn't like an abrupt change. So it so happens that Vc plus was equal to Vc minus. That's what we had further up here. Vc plus equal Vc minus. This is what we argued based on the fact that the capacitor does not like a sudden change in its voltage. And Vc minus was what the problem had already given us at the beginning. In this case, Vc of 0 plus, sorry, I think I said Vc plus and minus. I meant Vc 0 plus equals Vc of 0 minus. So let's apply the condition. So if I put Vc of 0 plus, which just, well, let me put it like this first. A e to the minus t, well, I replace t by 0 plus, which is still 0 as far as calculating the exponential is concerned, plus v naught. What is the exponential of minus 0? It's exponential of 0. What's the exponential of 0? 1. So that's simply a plus v naught. And because this was the same as Vc 0 minus in this case, so A is simply v naught minus Vc 0 minus. So there you go. The solution is complete. Vc of t is oh, I'm sorry, minus v naught plus, like that, right? Yeah, thank you. Now it's correct? Yeah. And this is for all t greater than 0. So this is just a constant that happens to be something that had to do with the value of that battery voltage source that you had there, plus minus that, plus whatever the initial voltage of the capacitor was. And that's multiplying a decaying exponential. So after a very, very long time, in theory infinite time, this term has vanished, and the capacitor has become fully charged to voltage V naught. Yes. So now if I were to put everything together and plot this on the entire time axis, this is what I'd see. So before t equals 0, the capacitor was charged to some Vc of 0 minus. So this is Vc as a function of time, right? So all the way to this point, 0 minus. And then this is the point 0 plus, which is infinitesimally close to the vertical axis. We saw that during the transition from 0 minus to 0 plus, the capacitor voltage did not change. So your Vc of 0 plus was the same as Vc of 0 minus. And then after that, you have an exponential decay. And eventually, maybe I should be give myself a little more space. Eventually, after a very long time, this is an asymptotic behavior. So after a very, very long time, the exponential term has evaporated, and I'm left with V naught. In this case, I assume that Vc of 0 minus was a value greater than V naught, the way I've drawn this. Okay. So now we introduced a concept here, that tau. So I want to go back to it here. This is where I introduced the general solution to these first order equations. When you have a first order circuit like this, described by a first order differential equation, and the answer following an exponential decay like this, that parameter, that factor that comes out in the denominator of t is called time constant. And this is, by the way, a very, very generally useful and widely used concept in all science and engineering. Not just in electricity. Okay. Now, what is the exponential of -1? Can someone punch that in their calculator or put it in Google? Or maybe you know it. What's the exponential of -1? Well, what is the exponential of something? It's e to that power, right? So e to the -1 is 1 over e. What's the value of e? 2.7 or something, right? So what's 1 over 2.7? A little less than 0.5, right? It's more like 0.3 something. I think it's closer to 0.36, okay? So if I put t equal tau in that equation, so if I look at the value of Vc after time t equal tau, after one time constant, the decaying part, the exponential part, has dropped to 0.36 of its initial value. So let's write that as the definition of the time constant. The time after which the exponentially decaying portion of the function, the variable of interest, has dropped to approximately 36% of the value of that chunk. And this is because e to the minus tau over tau, which is, so if you replace t with tau, e to the minus 1 is approximately. Okay. And if you give it more time, you go one more time constant or another time constant, you will see that this exponential becomes smaller and smaller, to the point that very often practically after a few time constants you would say the decay has fully taken place and I've reached, for practical purposes, a steady state. And you know, how long you really have to wait depends on how much accuracy you want, right? But very often 5 times the time constant or 10 times the time constant happens to be enough. And so this kind of thing is very commonly used to tell you about the reaction speed of a system. So you can imagine, for instance, if your computer processor is working at 1 gigahertz, which means it's going, it has to have at least one cycle, let's say, every nanosecond, right? It means that the time constants of the circuits involved in it should be significantly smaller than a nanosecond, so that all the capacitors involved have time to charge and discharge. I think you had this example in the lab where you looked at an RC circuit similar to this, where you saw that in one case your circuit had enough time for the capacitor to charge during each cycle, but then when you increased the resistor, the value of the resistor by a factor of 10, your RC went up by a factor of 10, and you didn't have the time, or the circuit didn't have the time for full charging and discharging. Did many of you see this in your lab? Yeah. So this is that effect. So this is the time constant. And the concept of initial value and final value is something that, again, you would readily see from this equation. So the initial value, if you're talking about this VC equals a e to the minus t over tau plus b, well, at time t equals 0, this initial value, in this case, is a plus b, because the exponential of 0 is 1. Its final value, after the whole thing has decayed to complete DC steady state, the first term has disappeared and b has become the answer. So in this case, a plus b is the initial value, and b is the final value. Okay? And I think this is where we have to stop it. So until next time, thank you.